Okay, hello, I'm recording now. So today our task will be to do two things. And this is, we are still in chapter 3 of Katzlender. We want to define pseudo-random generator, what pseudorandom generators are, and use them to construct stream cipher, where the messages are much longer than keys. Okay. Yeah. And this is not some theoretical construction that is just, given for illustrative purposes. It's an actual construction. This is how actually stream ciphers work. Okay. So, well, I need to recall this notion that two random variables, D0 and D1, are called indistinguishable, and that's a computational notion, computationally indistinguishable, if for all efficient algorithms, okay, so A is some algorithm, it holds that the probability of A on input X, that A says 1, okay, outputs a bit 1 on input X, where X is taken from this first distribution. If I contrast it with the probability that A on input X outputs 1, where X is taken from the second distribution, and if I compare them, then this needs to be a negligible function of the security parameter. So to be fully formal, these distributions must be functions of security parameter as well. Okay, so for example, let's say these are all encryptions of some fixed n-bit message, and these are all encryptions of some other n-bit message, where these are random variables, because an encryption of some even fixed message is a random variable going over the choice of the key and the randomness in an encryption. So, both of them are functions of the security parameter n, which is the length of the message. And if I construct encryptions correctly, then it should be the case that if I take that any efficient attacker, when he gets X from the first distribution, which is random encryptions of some first message, and you measure the probability that it says yes, okay, or 1, and you compare it to the probability that he says the same thing, but on an input which is random, which is this random variable. So for example, random encryptions of some other message. And maybe this difference is not 0, meaning that the probability of doing this and the probability of doing that are identical. But even if this difference is non-zero, it is very tiny. It's a negligible function of the security parameter. So it's a very fast vanishing function. Meaning it can be set arbitrarily small for, just you have to hike up security parameter large enough. Now recall, so this is the first notion of general indistinguishability of random variables. Moreover, recall that E is called, encryption scheme, encryption E, okay, so I would skip all the other syntax, that you also have to have decryption, you have to have key space, and so forth. I would view this as implicit. Encryption E is indistinguishable secure if for all two messages M0 and M1 in the message space, the variable of KM0, which is a random variable defined by a random choice of the key in the key space, is, again, are indistinguishable computationally, and this is denoted that D0 is like this. Okay, so we will say D0 wavy equal C on top D1, and we'll read this as random variable D0 is computationally indistinguishable from a random variable D1. And the intuitive meaning is that any efficient adversary, any efficient algorithm which has inputs from here acts indistinguishably, so only negligibly different from the same algorithm given an input from here. This is exactly what this means. Feed this guy a random variable like this, or feed this guy a random variable like this, and you cannot tell the difference between how this guy acts as long as he is efficient. And sorry for using sexist terminology of calling algorithm he. Okay, so it's like, next time I will call it she. All right. So here is, truly I should call it it, but that's fine. All right. So here is a requirement that encryption is indistinguishably secure. For any two messages, a random encryption of the first message is indistinguishable from random encryption of the second message. Okay. And you should be by now getting the intuition that what this means is that any attacker which is given a thing formed like this, so a random encryption of M0, acts indistinguishably from the same attacker algorithm who is given this. And when you read the book, you will see that that notion is, it can also be stated as semantic security, because this, semantics is like a study of meaning of our language, right, as opposed to syntax. And the meaning is something that you can, that this gives you something. It gives you some information. Some written statement or spoken statement, right, conveys information. So it has some semantics, meaning somebody can use it in some way, right? Can derive information from it. It somehow changes their life to, read something and comprehend it. It changes them in some significant, in some way. But a ciphertext basically cannot change anyone. Any attacker, any efficient algorithm, given a random stuff formed like this, acts indistinguishably from the same attacker given things like this. So therefore, these things are useless, right? There cannot be an attacker that does anything meaningful with the ciphertext because of this notion, right? If these ciphertext forms like this and a ciphertext form like that are indistinguishable, this means that any efficient algorithm will not act any differently except for negligible probability, given an encryption of M0 and versus given an encryption of M1. So we can give these encryptions because nobody basically can make any sense out of them. That's the meaning of this notion. Okay, so this was, a fast, perhaps, or perhaps not so fast, but a recall of where we were. Okay, so now, what are pseudorandom generators? Abbreviated Prgs. Okay, Prg is an efficient, meaning polynomial time, deterministic algorithm. So it's not randomized, it's on fixed input, it will always have the same output. Okay? Such that it's a deterministic algorithm. Let's denote this algorithm G for a generator, which meets two criteria. First of all, there exist some first of all, for every input, for every bit string X, if I measure the size of the output of G on X, it is strictly larger than the size of the input. And what this means is that, i.e., given n-bit string, n-bit input X, G, Y, which is G of X, must have more than n bits. Which means that G expands. The input it receives, right? So here is some bit strings which you give to G. G works and outputs a bit string Y, and it has to be that Y is larger than X. Okay. So it's a simple syntactic property. Give the guy n bits, he's splitting n plus something bits. Secondly, and this is a security property, so this is a syntactic property. Sorry. I see that it's not focused very well. Focus better. Okay. So secondly, if I look at the distributions of output of G, when I give him inputs which are random n-bit strings, okay. You know what? And we actually, it's not enough, sorry, that it's just longer. It has to be regular in some way. Sorry. Specifically, there must be some polynomial P, let's such that P of n is greater than n for every n, and for every X, which is an n-bit string, the size of G output on this n-bit string is equal to Pn. Okay, so if X has n bits, then Y has P of n bits. Okay, and this and the Pn has to be larger than n. Okay. Hold on, sorry. Okay. So now a security. This means that it expands, and it expands in a regular way. Given any n bits, it gives you p of n bits for some polynomial, a p. So, think of this polynomial as, for example, n plus 100 or n square. Okay, or yeah. So whatever, but larger than n always. And the second requirement is that G's outputs on random inputs are indistinguishable from random strings. G output on a random input is indistinguishable from a random string. I.e., if I look at the outputs of G, when I feed him random n-bit string, okay? So the experiment is I pick a random n-bit string, feed him to G, and see what comes out. Then this output is indistinguishable from a truly random bit string of the appropriate length. So Y, which is a random bit string of length P of n. Let's have a notation that UN is a uniform distribution over n-bit strings. Then I can rewrite this as G of X for X taken from UN, okay, random n-bit strings, is indistinguishable from U Pn, random Pn bit strings. Okay, so example, P of n is n plus 1000. Okay, that's a polynomial, and it's always P of n is always larger than n. Then outputs of G on inputs which are random n-bit strings are indistinguishable from random n plus 1000 bit strings. Okay. Okay. Constructing a PRG is not easy. It's not obvious how to construct such a thing. Let me just give you some examples for like what it would not be a PRG. Okay. So bad examples. It's always good to give to young people bad examples. So let's say G given X just outputs X concatenated with X. Okay, how about that? Okay. So clearly output of G is twice the length of the input of G, right? So P of n is just 2n. Okay, so expansion is satisfied. However many bits I gave G, its outputs on those many bits is twice more. Okay. But look at what do strings that are output by G, what do they look like? So let's feed G with random n-bit string. And let's see what it outputs, right? So by definition of what G does, these strings look like this. It's X concatenated with X for X, which is a random n-bit string. And now I ask you, is it true that such a thing is computationally indistinguishable from a real random bit string of appropriate length, which is 2n bits? Is this true? What is computational indistinguishability? That means that for every efficient, take, is it true that for any efficient algorithm A, is it true that when he's getting a string like this, X comma X, for X, which is a random n bits, that he is really going to output the same type of output compared to the situation which is in this case, where Y is a true 2n-bit random string? I say no. It's very easy to show an efficient attacker that immediately distinguishes between strings formed like this and strings formed like this. What is that attack? So I want an attacker, an algorithm, which will distinguish these type of strings from these type of strings. What should this attacker do? It's something very, very simple. He needs to output some judgment, okay? Let's say 1, based on something about these strings. And I want an attacker that distinguishes these from these. So his output is very different in this case and a very different in this case. See if the same string twice, exactly. So take any, consider the following such that A on input Y outputs 1 if and only if, so if and only if Y left equals Y right, where Y is parsed as the left side and the right side, so both of them n bits. Okay, so this is the notation we will use often when you have a bit string that has even number of bits. Bit string, let's say Y, YL stands for the left side of the left half of those bits, and YR for the right half of the bits. So it returns 1 if then and 0 otherwise. Okay, and now why is it a bad example? So this attacker works, right? It distinguishes these two. Note, probability that A given outputs of G says 1 when we give when this probability has to go over random input is the probability that A on simply XX gives Y, right? 1, right? Because that's by definition of what the G is. G is this trivial algorithm that just tries to output X, X. Okay, and now the way we wrote A is that in this case, when it gets a string formed like this, it is falls into this case, right? So it's going to output 1. So this probability is 1. It always outputs on these inputs, it always outputs 1 on inputs formed in this way. Second thing, because okay, so so that's how A is going to work on outputs of G. And now compare to what does A do when he's getting a random string? When we take a random string from that has length 2n, well, the probability that it will output 1 is the probability that this random bit string happens to have left and right equal. So this is the probability that y left is equal to y right, right? Because that's the only case in which A outputs 1 on input y. Well, so what is the probability that if you take random 2n bits, the left and the right half of those bits equal? Well, this probability is 1 into 2 to the n, right? Because no matter what the left bits are, the probability the right bits are equal is 6. So A, destroys this PRG attempt because the difference between which A acts on outputs of G and the way A acts on random strings is because the difference between these two is not negligible, right? This function is basically almost 1. And no matter how big n is, in fact, the longer the n, the closer to 1. So it's not fast vanishing. It's basically actually very high, right? So the advantage 1 is the maximum, and this is almost that. It is convenient to use the following notation when talking about crypto systems. And here the PRG is our example of of a cryptographic crypto system or a cryptographic primitive. It is if A is an attacker against the PRG property of algorithm G, then we'll define advantage of A against G in the PRG game as a function of the security parameter, so length of inputs to the PRG, and we'll define it as this difference that between this probability, between how A acts on this and how A acts on these two distributions. So it's the difference between the probability that A on outputs of G says 1 when this probability goes over random inputs of G, and the difference between the probability that A on random strings outputs 1, where these are random strings from the proper of G whose expansion is Pn. So this is expansion polynomial of G. Okay, and absolute value. So this value is the advantage of A against G in a PRG game. And this advantage is almost 1. Okay, and basically 0 advantage is perfect. I mean, meaning that A completely fails. 1 advantage is A completely wins. Okay. Using this notation, we basically say that G is a PRG if for all efficient attackers A, this advantage is a negligible function. Right? Okay, so this trivial attempt at building a PRG does not work. So I guess this is the first bad example. Bad examples continued. Okay, let's say that we somehow want to stuff the bits. Well, so how about G of X picks random n-bit string R, where n is the length of the input string, and outputs y, which is x comma r. So maybe this went too fast and not everybody remembers, but why is this? Okay, so it's expanding because right, the length of y is to the n if the length of x is n, and actually it's pseudo-random. It has perfectly random outputs. On random input. Right, because, well, if I give him a random input x, then x is a random string and r is an independent random string, so y is a random 2n-bit string. So what's wrong with this? Why is this not a PRG? Don't know if anyone remembers it, because it was a requirement that was set a few white sheets ago. Anybody remembers why this would not, why this is a no-go? Yes, but it's not deterministic. Okay, so you cannot just add some random bits. The only randomness you have is the input, and you only have these n random bits to work with. So note that since G is a deterministic function, okay, so another kind of easy type of, how about G of X, therefore pads x with some deterministic bits, okay, or x comma 0 or x comma c for any constant c. Okay, well, it expands, but in a bad way, right? So A can tell G's outputs from random bit strings easily. Output 1 if input has if input's last bit is 1, right? And it works for all those cases, right? If the input ends with this or it would end with that, I would just output 1, output 0 otherwise. Okay, A on g of x, the probability that it outputs 1 is 1, right? Because g of x always has 1 as its last bit. So if A, given an input, just tests for this property, it will perfectly, it will always recognize outputs of g. But probability that A on a random string outputs 1. Okay, so this is n plus 1 because the output has has 1 more bit than the input. Well, that probability is 1/2, right? Because, okay, well, half of random bit strings do have this form. Half of them do end with bit 1. And this difference between how he acts on outputs of G and how he acts on random bit strings is distinguishable, right? Because 1 minus 1/2 is 1/2, which is not negligible. So we cannot basically any strategy which would say, okay, take some bits of x and copy them. Well, that would fail basically, right? Because the test is going to just test whether, you know, some bit on the left-hand side and some bit on the right-hand side are the same. Adding some fixed bits does not work either. Anything that, you know, as long as, you know, if you just take x and add some sort of function of x, well, G is the public algorithm, right? So no obscurity with no security by obscurity. So that function is part of the G algorithm. So I can compute the same function and test for it. So you can say, well, so how is it possible? Well, no, you have to take the inputs and compute some function, but not output the input itself. Just compute that, output that function of x. Okay. Here is the space of all inputs of G. Okay. It will, G is a function, right? So its outputs are P of n long. The domain has 2 to the n elements, and the range has 2 to the P of n elements. Right, the domain and the range. Now, so, and G is a deterministic function. So the size of the image of the domain is some subsets. Okay, let's call it like this. This is the image of x. Okay, so this is basically, okay, I can denote it like this. Okay, meaning all the values that look like this for some x in the domain. Now, note that the size of the output space of the image of the so the what is it called? Not codomain, but codomain is all of this. But the image of the domain, it's at most 2 to the n elements, right? Because well, it cannot be more, because for each of these guys I get unique value because G is deterministic. And without loss of generality, it could be less because perhaps G also has some collisions. But even if G does not have collisions, then the best thing is that it has this is 2 to the n elements. Note that the size of the output space, of the real output space of G, compared to the size of the domain, of the codomain, is therefore at best 2 to the n divided by 2 to the p of n. So if this PRG is doing, a lot of work, so this is 2 to the 1 over 2 to the p of n minus n, right? So if p of n is, just a little bit larger than n, this is going to be a negligible amount, right? So this means that if I take a random strings of this length, then it's a negligible chance that that string happens to be the output of G. So outputs of G are in no way distributed like real random P of n bit strings, because a real P of n bit string is a random choice of something in here, right? And it is with the negligible probability that such a thing actually is an output of G. And yet we ask that an efficient algorithm, any efficient algorithm, which is given some random Pn bit string, cannot distinguish that from a random string that is chosen from this tiny subset, namely those strings which are outputs of G. You can also see that there is no way that you can satisfy this you have to ask that this can only happen, this inability to distinguish a string that is randomly chosen from the big space, from a space that is outputs of G. This inability can only hold for algorithms which are polynomial time. Because if you had an exponential algorithm, here's what he would do, or what this algorithm would do. It would just, given any string, any y, it would search through all possible 2 to the n inputs of G and apply G forward and test, therefore, whether the strings that he gets, is it part of the subset? It is a public function and is deterministic. So in 2 to the n time, an attacker can compute all values here and compare to the value at hand. If that value is not here, he says 0. If that value is here, he says 1. So there always exists 2 to the n time attacker on PRG, on a PRG, given y in the output, in the possible output space, right? Test if there exists x in the input space such that g of x gives you this y. If yes, output 1. If no, output 0. And so the probability that he makes a mistake is only this, right? It's the probability that a random string happens to be an output of in the space of outputs of G, which for any large Pn is actually negligible. Even for Pn, which is simply n plus 1, this probability is 1/2. So the probability that he says it's pseudo-random on a random string is 1/2, whereas on a pseudo-random string he always says. So his advantage is still 1/2 in that case. And the only thing is that this takes to the dn time, right? This testing. So, okay, but so you know what? Wait till next week or read up for how such PRG could be constructed. And actually, we don't even give a full construction. We just show, well, okay, we'll show you a little bit of like how it could possibly be constructed. Today, assume PRG exists with expansion. Assume PRG exists, so we'll call it G. With the expansion P of n, okay? We'll show how to use it to encrypt. Okay. So let G. So here is the string cipher construction. Let G takes n bits and outputs Pn bits be a PRG. Let key space be n bits. So a random key is will be an input to a PRG, and the message space will be P of n bit string. So an output, the same space as outputs of a PRG. And let encryption, given a key and a message, key is n bit long, message is p bit long, run the key as an input to a PRG. And what do we know of the output? The output will be pn bit long. So we are going to do what a one-time pad does. Take the output of the PRG and XOR it with the message. And let decryption, given a key and a cipher, reverse this process. So expand the key using a PRG and XOR with the cipher text. Okay, correctness is immediate decryption of encryption of M is K, is G of K is going to be equal to Prg expansion of G, XOR with, and what is an encryption? Prg expansion of the key, XOR with M. So the two expansion cancel out, and this is just M, right? So basically, stream cipher is like one-time pad, but using G of K instead of K directly, right? We are instead of taking the key, we are first expanding it with the Prg, and we use this expansion as a one-time pad. Okay. Well, so decryption cancels encryption. How about efficiency? Is it efficient? Yes, it is, because G is a polynomial algorithm. So encryption is just exactly as efficient as Prg operation. Okay. Here is a statement theorem about it. Okay. If G is a secure Prg, then this encryption is an indistinguishable encryption. And note, the size of the message space is 2 to the p of n, and the size of the key space is 2 to the n. So the message space is much, much larger than the key space. Well, how much larger, depending on how big p of n is, right? But we will show next week that if Prgs exist at all, then basically there's no limit to how big this expansion is. So even if you have a Prg that expands just a little bit, then you can harness it and run it in a loop and make this p of n as big as you want. So if n is 100, p of n, it's 100 bits of a key material. P of n can be, hundreds of billions if you want. Okay. So that would be really lovely, right? Because we are breaking through the one-time pad perfect secrecy barrier. Okay. So how do we argue this proposition? All right. Here is the construction, and let me, so for E to be indistinguishable, we have to test if we have to argue that for all messages M0 and M1 in the message space, which in this case is p of n bit strings, the distribution of encryptions of M0 are indistinguishable from distributions of encryptions of M1. Okay. So, okay, but by construction of E, here is that construction above. By construction of this encryption E, let's call this distribution D0. These are random encryption of M0 for any fixed, let's fix two messages, M0 and M1. Consider random encryption of M0, call that D0 distribution. Consider random encryption of the other message M1, call that the D1 distribution. By construction of E, this D0 distribution is what? Well, what is E of K of M0? Well, E of K M0 is G of K XOR M0. So this is outputs of a PRG XORed with M0, where key is a random in a key space, but what is the key space? It's a random bit string. So we're just taking K as a random n-bit string. And D1 is by the same token, right? Because really it doesn't matter whether I'm encrypting M0 or M1. It's going to be the same process, just applied to M1. Okay, so that's what I want to argue are, I hope that these two are indistinguishable. But what do I know? I know that G is a PRG. Let me bring up what the fact that G is a PRG. What was it supposed to mean? It was supposed to mean that outputs of G are indistinguishable from P n-bit strings. So if I got my hands on this variable, it is indistinguishable from a random bit string of length Pn. So by the fact that G is a PRG, we know that the strings that look like this, random outputs of a PRG, are indistinguishable from random P n-bit strings. So it follows, and a formal argument is actually called is a reduction, so-called reduction from one problem to another. In the book, okay, but maybe we'll say this at the end of the lecture. I'm not really sure that we have enough time. It follows that for any M0, the distribution that looks like this, so this says that if you take a string like this and give it to some efficient algorithm, then that algorithm cannot do anything significantly different from what it does on a fully random string. What I will skip here is the formal argument why this implies that the following two distributions are also indistinguishable. An XOR between G of K and some fixed message M0, because that will work for any M0, and XOR between a random, fully random value So this distribution is over k's, which are random n-bit string, and this one is over y's, which are uniform p n-bit strings. This is the assumption. And this is a consequence. Proof skipped for now. But for now. Okay, but let me give you an intuition why this proof goes through. So look, this says that if you give any efficient attacker, any efficient adversary, any efficient algorithm, a string that looks like g of k for a random k n-bit string k, then he acts no different, except for negligible difference, from what he does when he gets a truly random p of n-bit string y. This says that if you give him a string formed like in this way, but XORed with some M0, then he cannot act any different from when he gets a random string like this, and also XORed with M0. So all I'm saying is that if strings like this, g of k for a random k, looked indistinguishable from strings like this, y, which y is truly random p n-bit string, then it also is the case that these type of strings XORed with a fixed value are indistinguishable from these strings XORed with a fixed value. Okay. Okay. Let's take this. If perhaps you see the intuition for how you would argue this from that. Perhaps you don't yet. This is in the book. Perhaps we'll get to it either today or next time. Okay, but let's take this at faith for now. Then, okay, well, this is the distribution D0. And let me call this distribution, let's call it R0. My name for this distribution. Similarly, of course, because for M1, because this argument really doesn't have anything to do, doesn't really care what this value of M0 is, it will also be the case that distribution that looks like this, XOR GK with M1, and this is the D1 distribution, it's also indistinguishable from a truly random string XORed with M1. Okay, and let's call this distribution R1. Okay. Okay. I want to argue that D0 is indistinguishable from D1, and believe me, and we'll come back to this, that the assumption that G is a PRG implies both this statement and this one. In fact, it implies a statement like this or like that for any message M, for any fixed bit string M. So therefore, in particular, if you instantiate M as M0, it holds. If you instantiate M as M1, it also holds. Now note that R0 what is R0? It's a fixed bit string XORed with a uniform PN bit string. R0 is identical to a uniform bit string. And this is by the one-time pad argument. Right? For M0 is fixed. There is some two messages that I'm interested in. I want to break this encryption of some two messages. But if random encryptions of the first message are indistinguishable from essentially a one-time pad encryption of this first message, then by one-time pad security argument, the one-time pad encryptions of any message are indistinguishable from random bit strings. And of course, the same goes for the other message. So an R1 is also identical to a uniform bit string. So call it fact 1, call it fact 2, and call these things fact 3. And now, basically, the following is the case. R0, these are one-time pad encryption of M0, is identical to R1, which is one-time pad encryptions of M1. And R0, and this is by 3 and 4, by 3, right? Because both of them are equal to random PN bit strings. So in particular, these two are identical. They're both equal to random bit strings. And this R0 by fact 1 is indistinguishable from outputs of an encryption on M0. So this is by fact 1. But this thing is indistinguishable from random encryptions of M1. Sorry, I'm focusing refocusing the camera. So I wanted to give it a little more light. Okay. So indistinguishability is transitive. Meaning, if no efficient attacker can distinguish this random variable from that one, and well, no efficient attacker can distinguish this random variable from that one because actually they are identical. So no attacker of any computational capabilities can distinguish them. But also this one, no efficient attacker can distinguish from that one. Then it follows. So 1, 2, this is the statement 2, and 3 imply that D0 is indistinguishable from D1. Okay, so so these two are computationally indistinguishable as a consequence. I don't have time right now to convince you that the PRG, to convince anybody who doesn't believe how or doesn't quite see how it will be argued, that if random strings like this are indistinguishable from strings like this, then also taking a string from here and XORing with M0 is an indistinguishable object from an object formed by taking a string from here and XORing with M0. And in fact, whether it was M0 or M1 doesn't matter. So an object formed by taking string from here and XORing with M1 is also indistinguishable from an object formed by taking a string from here and XORing with M1. You can read in the book a very nice description, and we will show this next time, that this is indeed the case. And now, if you believe that these two are consequences of the G being a PRG, then what they basically say is that no efficient attacker algorithm can distinguish output of the stream cipher encryption on M0 from an output of a one-time pad encryption on M0. And likewise, they cannot distinguish a stream cipher encryption of M1 from a one-time pad encryption of M1. And if no efficient attacker can distinguish these two, and also cannot distinguish these two, and it is the case that these two are identical, so in particular, he cannot distinguish between these two, then it follows that he cannot distinguish between these two as well. That part is not that hard. If you assume that there is an attacker who can distinguish these two, then he must either act differently on these, or significantly differently on these, or significantly differently on these. Because if he acts significantly differently of these, the difference must be somewhere. And any of these facts would violate one of these three assumptions. Hence, machines that can distinguish these two cannot exist. Okay. This, this is a very abstract view of the stream cipher. Namely, it says, okay, how a stream cipher does it is that it has to have some PRG inside it that will take the key and expand it. And this expansion will have to be XORed with the message. And that's a secure way to encrypt. That's what's claimed by this theorem. There is, of course, questions like how does this PRG can be constructed? And also, particularly, what kind of construction would allow the stream cipher to be really useful? Okay, because you can imagine forms of expansion of the key that wouldn't be that useful in many applications. We'll come back to this next week to both points. Okay. I will switch off recording so you can ask questions if you want to more easily. And otherwise, I'll see you next time.